Recall that we first began our discussion of section 4.2, examining composition. But what does that have to do with inverse functions? Well, it turns out that composition is a tool that we can use to algebraically verify if a pair of functions are, in fact, inverses. Here's how it works. For inverse functions f of x and f inverse of x, it is always true that f composed with f inverse of x equals x, and f inverse composed with f of x equals x. So notice we're using composition here to verify inverse functions. To understand what this is stating, first recall that we said in general composition is not commutative. That is, if I switch the order of my functions, I don't get the same output. But in the case of inverse functions, we will get the same output. Now let's examine that second statement, f inverse of f of x, using a mapping. So suppose this is the domain of f, and we're going to map that to the range of f. So we're going to start with some sort of input from f, we'll call it x, and we're going to apply the function f to get some sort of output, we'll just call that f of x. So looking at this statement, f composed with f inverse of x, if we do f, I think I said it backwards, f inverse of f of x means f inverse of f of x. So I'm going to start with some sort of input to f. That's what I have right here. That input is called x. And the output we're calling f of x. Now, once I execute that, if I immediately turn around and apply f inverse to that, well, look at the mapping. If I apply f inverse to what I got the first time around, it's going to take me right back to where I began. So applying a function and its inverse successively really doesn't get us anywhere. What we start out with, the original input, turns out to be the ultimate output. That's because a function and its inverse have exactly the opposite operations. So it's sort of like I add 2 to a number and then immediately subtract 2. I don't get anywhere. I have my original input. So to determine if two functions are inverses, we compose them in both directions to see if we get x. Let's try this on example 10. Use composition to algebraically determine if the following pairs of functions are inverses. So we want to compose them in both orders. Let's just start with the order f composed with g of x. So we're going to break it down into f as our outside function and g as our inside function. As we've been practicing, we start on the inside function and we're going to replace g of x with its function rule. So inside parentheses here, I'm completely replacing g of x with its rule. Then we're going to go to the function called f, and we're going to use that function rule next. And whatever we have in parentheses, we're going to replace the argument or the variable with that argument. So we're going to have 2 times the argument, 1/2 x minus 2 plus 4. Now, everything's plugged in. Let's simplify. When we distribute R2, 2 times 1/2 x gives me 1x. 2 times negative 2 is negative 4, and we have a plus 4 on the end. Notice negative 4 and plus 4 cancel, and we end up with x. So in this direction, what we can see is that if we plug in x and we apply g and then immediately apply f, we end up with the same output. So we didn't get anywhere. Now, these two functions appear to be inverses, but it only is a solid proof if you can prove it in both directions. That is, we need to also show that g composed with f of x is equal to x. So this time, g is going to be our outside function, and f will be our inside function. So postponing g to the next step, we replace f with its rule, which is 2x plus 4. Then we're going to go to the function g and find the variable, and we're going to put our argument, what's inside parentheses, into that box. So we're going to end up with 1/2 times the argument 2x plus 4 minus 2. Now, distributing our 1/2 to simplify, we have x plus 2 minus 2, which gives us just x. So once again, we see that if we plug in x and first apply f and then apply g, our output is the same. Because we have composed these functions in both orders and got x in both directions, we can conclude that our functions are inverses. So I'm going to say, therefore, those 3 little dots in math, when you see those, that means therefore. Therefore, f and g are inverses. Let's try this same procedure on the next example. We have f of x equals 4x minus 1 and g of x equals 1/4 x plus 1. Now, just looking at these two functions, using our intuition, you might observe this one multiplies by 4, this one divides by 4. Those are opposite operations. Also, this one subtracts 1, this one adds 1. They seem to be opposites. So if I were using my intuition, I might say, yeah, they kind of look like inverses. But we want to prove it algebraically. So let's see what happens when we compose these two functions. F composed with g of x. That is f of g of x. So I'm going to replace g of x with its rule, 1/4 x plus 1. Then we're going to take that argument to the function f and plug it in for the variable. So we have 4 times 1/4 x plus 1 minus 1. Simplifying by distributing first our 4. 4 times 1/4 x gives us 1x. 4 times 1 gives us 4, and we have a minus 1 outside parentheses. Now, simplifying, we end up with x plus 3. Notice that's not x. So because I did not get out x, we can automatically conclude that f and g are not inverses. We don't have to do any more work. We can say f and g are not inverses. Kind of like that direction because you have to do less work, right? You only have to show it one way. So why were they not inverses? If we rewrite our function f in terms of transformations, we might consider it as 4 times x minus 1/4. That's equivalent to 4x minus 1. So yes, this one multiplies by 4 and this one divides by 4. This one adds 1, but this one subtracts 1/4. So thinking about it in terms of transformations, those are not inverses. If that's a little confusing to you, remember, we just proved it with composition. They are not inverses. Let's try example C. We have f of x equals x minus 1 to the 3rd power, and g is cube root of x plus 1. Again, just using our intuition, the first one cubes, the second one has a cube root. Those are opposites. We have a minus 1 inside parentheses and a plus 1 outside parentheses. So let's see if it turns out that these are inverse functions. And remember, we have to prove it with composition. F composed with g of x is f of g of x. Starting on the inside, we replace g of x with its rule, cube root of x plus 1. Then we're going to go to the function f and replace the variable with our new argument. So replacing the variable, we have cube root of x plus 1, and then we copy down the rest of the details of f, minus 1 to the 3rd power. When we simplify inside parentheses, the 1 and negative 1 cancel, leaving just behind cube root of x, and then the cube root of x cubed is x. So in this direction, they appear to be inverses, but remember, it's an incomplete proof unless we can show it both directions. So let's evaluate g of f of x. So g is going to be on the outside this time, f is on the inside. So postponing g, we replace f of x with its rule, that's x minus 1 cubed, and then we're going to go to the function called g, and we're going to replace the variable with our argument. So we're going to have cube root of, now I'm replacing the x with the argument, x minus 1 cubed, and then notice the plus 1 here is outside the function. So the cube root of something cubed is that something, or the radicand, And then notice the -1 and the +1 cancel, and we get x. So because we have composed these in both directions and we got x either way, we can say therefore, remember the 3 little dots mean therefore, maybe you saw that in high school geometry, therefore f and g are inverses. So if we were to graph f and g, we would see that they are perfect reflections of each other across that line, y equals x. So this is an interesting concept, and you may be wondering, what's the point of inverse functions? Who cares, right? So here's an interesting application of inverse functions to cryptography. Cryptography is the science of encoding or encrypting information. Inverse functions are used in cryptography to make information secure. So if you've ever bought anything online, maybe you're purchasing something on Amazon, you're sharing your credit card information, the information that's sent over the internet has to be encrypted in order to prevent someone from intercepting that information and using it in a wrong way. So that information is encrypted. To understand how that encryption occurs, here's a really simple example of how we might do that. Suppose we want to encode the password math so that no one who intercepts the message would be able to decipher it. Use the table below to convert the word math to a string of numbers. Then use the cipher function f of x to encode the message. So the first thing that we're going to do is take our password, which we want to keep secret, math, and we're going to convert it to a string of numbers. And we're going to do this in a really simple way. We're going to take our alphabet, letters A through Z, and equate them to a number. So when we see A, that's going to represent number 1. B is going to represent number 2, so on and so forth until we get to Z, which represents the number 26. Now, we don't ordinarily do this with our alphabet, but other languages, such as Greek and Hebrew, they have numerical equivalencies to their letters, which gives rise to some interesting studies. But anyway, we have our alphanumeric equivalency here. So what we're going to do is take our password, M-A-T-H, and we're going to rewrite it as a code of numbers. So notice M is going to be equal to 13, so we'll convert M to 13. A is equal to 1. T is going to be 20. And H is going to be 8. Now, that code is not too difficult to crack. So what we want to do is encrypt this information. We're going to use our cipher function or our encoding function. Our encoding function is f of x equals x cubed plus 1. So we're going to start with 13 and plug 13 in for x. 13 cubed plus 1 gives us 2,198. Plugging in 1 next, 1 to the 3rd power plus 1 gives us 2. 20 to the 3rd power plus 1 gives us 801. And 8 to the 3rd power plus 1 gives us 513. That is our encrypted message. That's going to be the message that we send. Message sent. So if someone encounters this string of numbers, first of all, they're going to have to figure out where does the letter start and end. Notice some of those are 4-digit numbers, some are 1, some are 3. What is the cipher function and what was the original equivalency between the numbers and the letters? So we have encoded the information. Now, the receiver is going to have the decoding function. The decoding function is the inverse of f. And notice here, f inverse is given as the cube root of x minus 1. So when the receiver gets the number 2198 and plugs it into that inverse function, they can convert it back to 13. F inverse of 2, the cube root of 2 minus 1 is 1. F inverse of 801 is 20, and F inverse of 513 is 8. Then that is the message received, or the message decoded. And then very simply, we can convert those numbers back to their equivalent letters to get the secret password M-A-T-H. This type of example is really oversimplified because, first of all, We're dealing with a really simple cipher function. Its inverse function is very easy to detect. Also, our alphanumeric equivalency is pretty obvious over here. And oftentimes, whenever you send information that is encrypted, it's got layers and layers of encryption. So there may be more than one cipher function, which would require more than one inverse function. But at least you have a sneak peek of the science of cryptography, which is really quite fascinating.